Everyone got their pizza? Okay, great. So yeah, I'll probably be relying just on basically you guys just giving the demonstration to yourselves here because I'm so tired. So I might just ask a lot of questions. First question, how many of you, first, are any of you like super new to functional programming? Show of hands. Okay. So how many of you who are more familiar with functional programming are familiar with the concept of extensible effects at all? Got one. And what, do you use Haskell or? Okay, so you're familiar with it in that context, okay. So it'll be very, very similar to that, basically the overall concepts, but it'll be in Scala, so that's what I'll be using to demonstrate that in. So I'll probably go very light into the actual details. I'm mainly going to be, I guess, setting up the context around the benefits of extensible effects, which means I'll probably actually just be covering that at the very end, basically setting up context around the problem that this aims to solve. So second question, how many of you are familiar with the concept of a monad? Okay, so maybe 30, maybe 50%, something like that. Does anyone want to give their definition of what they would? You gotta have this once per functional meetup. Someone trying to find the monad. Okay, I'll give a couple of brief descriptors here. So depending on from what angle you're trying to tackle this definition, you could have a variety of different definitions depending on whether you're trying to get into the depths of what it means to be a monad in category theory or what it means for a developer. But here are a couple of things that I've frequently thrown around in that context. Something that can flat map or bind, that's probably the most actual useful definition for you guys. Wrap around a value to hold a context. I like to use this terminology to help explain some of the variations in different types of monads sometimes. A monoid in the category of ender functors is probably the least useful definition for a monad, but you'll hear that referenced in category theory. But yeah, what's important here is map and flat map. Mainly flat map, because that's actually what is used to define the monad. So I'm going to be giving some brief descriptions into the different types of monads you might want to use, and some that you probably might not be familiar with, basically just to give the context around the problems that come up when you're dealing with nested monads and you're trying to compose things using nested monads of different types. So the either monad, you might hear this referred to as either, disjunction, or XOR, or different things depending on your language. Another show of hands, how many of you are familiar with the concept of an either? Okay, so yeah, this is one of the most basic monads you'll encounter very early on when you're working with these things. And basically what an either it allows you to hold the context of a value that might not have, you might have failed to determine. So the type parameters you'll see here in an either are the L and the R here are the left and the right values. So if you're trying to calculate a value that ends up with an integer, the R would be the integer, and the L would be whatever returns if you fail to derive that value. So it's frequently maybe just a throwable. And this allows you to treat those circumstances as actually being encapsulated within the actual data type instead of, for example, throwing that error. So either. If you want to, this is some syntax around constructing an either in Scala. You'll see here we're dealing with kind of the example I had just gone into, where you have an integer value you're dealing with, and the left value that you might return is a throwable. So you'll see these first two values defined as being a right, which means the value is present and you can operate on it, whereas the third value there is a left with a throwable in it. So when you're composing these things using a monadic for comprehension, as you'll see below. What you're basically saying is I'm going to provide the definition around how to manipulate and use these actual values, and the for comprehension will handle the context of the failure in the background. So what I mean by that is that you'll see this first example here, you're doing a for comprehension over those first two values, R1 and R2, and you're saying yield A plus B. So basically you're just saying add those two integers together, and that's going to yield a right of 3. And that's because both of those values were present and neither were left. So you'll look for that first value and then add the second value to it. But the second example, you'll see you have all 3 of those values there, where the third is that left. And you try to add all 3 values together, and you'll get a left value returned. And basically what this is saying is that you're saying how to add those values together, but in the background it's saying you weren't able to add that together because one of these values wasn't present. It was a throwable. So you'll look at that A value, you'll try and then you'll get the B value, and then you'll try and get the C value there, and you'll see that it's actually a left. So that's what gets returned, that left of the throwable. Any questions around the either here, or the use case it's trying to solve? Okay, great. Yeah, so I'm gonna be giving brief descriptions into these monads to try and give a context of working with them together. So the rider monad, show of hands, how many of you are familiar with that? Okay, handful again. So the rider monad, yeah, I'm expecting these hands to kind of dwindle as we go on because they're going to get into the more obscure monads. The rider monad here is a construct that's available in like Haskell, for example, but it's also available in Scala if you utilize one of the functional programming libraries such as Scala Z. And it basically says you have this context around this value which provides basically a logging mechanism. So instead of logging like inline in the code, you basically treat that log data as actual data that's encapsulated in this type. So you might be working on a value A, and you have a logging data type W. And basically what this will allow you to do is basically keep track of that logging information in the background while you're working on this type A. So you might have this type W just be a string, and I think my example is just going to show, again, working with like just integers. So yeah, you'll see here, this is utilizing the Scala Z library, and you'll see basically you're defining these values as tuples, where you'll see A here is defined as basically that pair is put inside the writer and the writer construct, and you'll see basically what that means is that that first value in that tuple is treated as the log value. So we're saying we're just dealing with the string we're accumulating, and that second value in that tuple is the actual value you're dealing with. So the writer of string event, the string is the log value, and the integer is the value you're working with. And again, this is a monad, so you're provided a map ability and a flat map. And if none of you are familiar with that, basically the map method allows you to provide to manipulate that underlying value in that monad by just providing a function on that type. So if you want to map on that, well, you'll see here, you just basically say, here's this function that says, take this integer and do something with it. And the flat map does something similar, except it takes the value and returns the monad again. So, and that flat map is basically defined as saying, accumulate these contexts in some way. So with the writer monad, when you do a flat map, what it's saying is you're going from this integer to this new writer of this new value. And what it'll say is that all you have to do is provide the function saying how to get to that new monad, new writer monad, and in the background it'll know what to do with that accumulating log value. So I'll get into the actual syntax of that in a second, but you'll see at the top here we have various ways of actually constructing a writer. And the first one is just using that writer constructor, and then the second one is implicit syntax allowing you to basically on any value say .set, and that'll basically lead to that value with the log data provided in the arguments of set. So that those first two are actually identical equivalent values. And that third one is basically just saying construct a writer with a unit value, basically just setting the log value. And then you have various ways to operate on this writer monad, which I might just gloss over here since not too many people are super familiar with this. But basically, the key point here is that with the writer monad, in order to operate on it as a monad, there has to be some implicit information available saying how do you want us to accumulate this log value. So since we're having the log value be a string in this case, there's an implicit, I'll throw a word out here, there's a semigroup. There's another functional concept, but basically it means that it'll tell when you're doing this flat map, it'll say, by default, it'll say how you want to accumulate that value. So basically, the default behavior for the string is just to basically append to that string. So when you're doing a flat map here at the bottom, you'll see this flat map on that a value, where you're saying, okay, take that a value, which is an integer, add 10 to it, and then you have this new log value, which is 10 added to value, we're saying here. And what this will mean is that since there's that implicit behavior in the background saying what to do with those strings, you don't have to say explicitly append to this string. It'll just by default have that semigroup logic in the background that says append to the string without you having to say it. So basically what this will yield, that flat map will yield a new writer with that string and that new integer, where the string is just the previous string with this new string appended to it. And you might actually want this, if you were using this in like production code, you might want this to be a list of strings or something similar to that. So yeah, that's the writer monad. Any questions about that?
Yeah, what are some of the benefits of using a writer compared to like either? When should I reach for a writer?
So the writer monad is when you're actually, so the writer monad differs from the either in that you have both values. It's not like an either or. You have both values. You have the log value and the actual value in the context. And what the writer monad provides is that flat map behavior that we want, which is such that if you define a semigroup for that log value, the flat map will automatically append and accumulate those log values together in some way. So if you're dealing with a list of strings here, there's also a default semigroup in the background that'll say, when you're flat mapping or using a for comprehension for these values, basically just append to that list of strings. Basically so that you'll see in a lot of cases, I know you'll want to accumulate different like log values relating to something, but then you don't want to pass around like a tuple. Because then you have to basically, for every single part of your code that's accumulating these values, you just say, okay, take this value, take the actual value, process it in this way, and then you have to explicitly say, take the log values and accumulate them in this way. So basically you'll say, okay, take the value, add this to it, blah, 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 take the two log values that we got from these different functions or whatever, and accumulate them by appending them into some list. So the writer monad provides a way for you to abstract that out, so you don't have to explicitly say how to accumulate those values. They'll just be accumulated in the background. Does that make sense to everyone? Okay, great. So that's the writer monad. The reader monad. So again, show of hands, familiarity here. Dwindling hands, 1, 2, okay. So the reader monad basically is an alternative way of providing a type of like dependency injection into a functional program. I'm not sure that's super common. I haven't seen it used in too many places, but basically it says you have this value A, but to get to that value, you have to provide a value E. What that means is that you can basically map over this monad and process, manipulate that value A or flat map into new readers and basically do all this processing on that A value without actually providing the configuration you require. You do that at the end, and you provide the configuration E. So I have the syntax here. So this is also a concept that you'll see in like Haskell. But to utilize this type of thing in Scala, you'll need to use that Scala Z functional library, or CATS, which I'll be showing an example of later on. So you'll see here, constructing this reader value, you have similar methods of just using the reader constructor, and basically it's basically kind of an abstraction around just a function. So you're saying you're providing this function in this first one, string to some value, and that'll basically mean that you this will yield a reader of string and int, where that integer is that s.length that you're operating on. And after successive processing on this reader will be such that you're operating on that value. So you'll say map, and you'll try and manipulate that integer value or do different things with it. That's the value you're going to be operating on. But the string type there is saying that you haven't provided that string yet. So once you're done doing all these manipulations on this function, then you can provide the string, and then they'll actually give you the actual value. And Scala Z actually provides this implicit syntax of using this ask, which will provide a, basically it's just a kind of a shell around the reader monad. So you'll see, so this third example, the C here, that's defined as ask with ID and string, so that you can kind of ignore the ID there. That's actually kind of irrelevant for this instance, but it's really basically a side effect of the reader having been defined recursively from the reader T, which is something I won't get into detail here. But basically, so what you're saying here is that you're going to be asking for a string, and then the value you're going to be working on, you want to map over that and get the length of that value. So that C is basically that integer value encapsulated in that reader string int is that length. And then but you haven't provided the string yet. So any questions around this reader here? I'm sorry. Okay, so I said I don't run into reader a lot. Do we run into reader T a lot? No. So basically, reader is actually just a type alias on reader T in the Scala Z functional library. So yeah, I don't run into, I haven't seen it used too frequently in Scala. I know it's more common to be used in Haskell in some places. But basically, you won't see it used too much in the more hybrid type of development shops because you'll lean, a lot of people will lean away from getting that deep into the functional approach because it'll become kind of syntactically heavy, and we'll get into that in a second, the reasons for that. So no, I don't run into the reader T a lot. Any questions, other questions on the reader? Okay. Oh yeah, by the way, when the retrieve there, so retrieving the value is just basically you take that reader and you say .run, and you provide the configuration you're looking for. So in this case, this is string is what you're looking for. So you provide that, and that a.run there that you'll see the value that'll be returned is just 4, because you can't just, that reader has been defined such that you're just getting the length there. Okay, transformers. So this is the first attempt to solve the problem that some of you might have guessed at when looking at these different monads. Does anyone have an idea? Well, first of all, show of hands, familiarity with the transformers, monad transformers. Okay, 1, 2. So yeah, anyone have an idea as to what problem this might be trying to solve after looking at those different monads? Any guesses? You don't win a prize, but okay. So you'll notice that as you gain more and more of these monads that you're working with, you might be working with 5 nested monads. You might imagine a scenario where you're working on a value and you need to have basically that dependency injection. So you'll have a reader, and then you'll have a log value contained in that value. So you'll have a reader of a writer, and then you might be working on an either as well. So reader, writer, either. And then you might also have a future in there. So basically you have this nested structure of monads. And if any of you are familiar with working with these types of things, you'll, I'm sure, be familiar with the pain points in that being just working with it is tedious, and that you'll need to do, several layers. If you're just doing a basic approach, you might just do several layers of maps. So you'll have dot map, dot map, the map, the map, six dot maps to get to the actual value you're operating on. Or if you're trying to, you might have the same thing with like flat maps. So you'll just have this nested structure of trying to get to the actual core value you're operating on. And basically what you want to do is just say dot map once and just have, be able to just operate on that value directly without having this nested structure. Does that make sense? People have run into that problem. So the more you get into the functional programming approach, the more you'll see more deeply nested monads, especially if you're utilizing in Scala these functional programming libraries, or if you're using Haskell. So the transformers, the monad so this is referring to the monad transformers, which is an attempt to solve that problem. And what it does is basically provides these constructs that wrap around a particular monad and say, basically it'll wrap around a monad. So if you have a monad of a monad, you'll have a monad transformer for that inner monad. And what that'll say is that you're wrapping both monads such that you can call map or flat map on that overall wrapped structure and get completely nested into the actual value. Is that a hand raised, or did I see? Okay, exhaustion, I'm saying things. So I'll just give an example here. Oh yeah, so this is just showing the problem that you'll see. This is a very tame example. This is actually a bad example because you can get much worse than this. But you'll see basically you have to do these nested maps, and it's a very trivial example of that. Not ideal though. Don't like it at all. So with the monad transformers, you'll see, for example here, the writer is another monad that's defined kind of recursively based on the writer T. So the writer is actually a type alias for a particular writer T. But what the writer T here is saying is that you have, for this first A value, you have two monads being worked on at the moment. You have this disjunction. So those two, forward, backward slash, that's the either in Scala Z. So you're saying that, so that's one monad, and then you have this other writer monad you're working with. So you have this context of a failure being possible, as well as the context of a log value being present. So you want to be able to do just one map over that whole structure to get to the core value here, which is 4, and operate on that. So in order to do that, you using the monad transformer approach, you would just basically wrap those two monads in this monad transformer. And this transformer here we're using is the writer T, the writer transformer. So basically once you have that either monad as well as that log value monad, the writer monad as well as the either monad there, you just wrap in a writer T, and then basically that writer T can just be mapped over or flat mapped or use a for comprehension, and you'll actually be kind of doing two maps or two flat maps at once. So you'll see for this first one here, composing it, well, it's not really composing it, but you're operating on it. Yeah, you'll see a.map, and you have this anonymous function here where you're just saying add 10 to the underlying value. So even though you have kind of two monads present, normally you'd have to do .map plus 10 to get to that integer value to operate on it. Whereas when you wrap in this writer transformer, you can just basically have that one map call. And then you'll see for the same second one here, if you're using flat map, instead of having to do nested flat map calls, you just do that one flat map call over that transformer. So basically just the transformers have their own map and flat map definitions that basically does that nested mapping and flat mapping for you in the background. So you'll see here, I show an example in this composition section here, where you're operating on 3 values in this for comprehension, and they have 2 contexts, one being the future and one being the writer. So instead of having to do like nested flat maps or whatever you might want to do, you can just do this. The for comprehension does the flat map for you in the background. So basically what this will end up doing is you're saying yield A plus B plus C. So all you're specifying is that you want to add those values. And then the for comprehension along with that writer transformer context is saying, okay, we know how to combine these features and we know how to combine these log values based on implicit definitions and scope. So basically, it'll combine those features by saying, run these things sequentially, and then it'll combine the writer monad by saying append to these log values as they're accumulated. Any questions there? Dylan?
For that for comprehension there, your transformers have to have the same first type argument?
Yes, so they all have to be the same. You have to have the same type signatures. So you have to be operating on a feature with a writer to compose them in this way. You can't just throw in like an either in there. Any other questions?
Yeah, I'm sorry. What is that symbol? There's like a / backslash.
Oh yeah, I should have just used the regular default Scala either here. That's the Scala Z either. It's called a disjunction. So that's basically saying the / backslash dash is just saying this is a write value with these values in it.
In your example here, you've got the nesting going like twice. If you go like 3 monads deep, will it handle that as well?
Yeah, so that's where it gets to be still painful. Less painful than if you're dealing with if you weren't using the transformers, because you can imagine how you'd have to handle that. With the transformers, you'd have to do subsequent nested levels of transformers, and then you could still utilize this comprehension in this way, such that it would say, for all of these different nested monads, I know how to successively operate on them. I'll do that for you. You just tell me how to handle the underlying values. So if you threw an either in here as well, you'd have to wrap that all in an either T. I think there's an either T, which is the either transformer, and then that would basically be the same, show the same as this, except it'd be saying in the background, okay, so we know how to accumulate these futures, basically run them sequentially. We know how to accumulate these log values, just append to them, and we know how to accumulate these either values, which is to say, get the first value, then get the second value and the third value, and if at any point along that way the value is not present and you have the left, stop processing. So basically, yeah, you'd have to do the nested transformers, but that logic would be handled for you still. But it does get less pretty, and you do end up with these abhorrent type signatures of nested transformers, which isn't ideal, but it's a step in the right direction in that you don't have to manually do these nested flat maps or comprehensions or stuff like that. Any other questions with the monad transformers here? Okay. Oh, and retrieving the values, you could just, with Scala Z, you just basically call .value to get the underlying value there, and but yeah, this is actually showing. Oh yeah, that's getting the values from the that's copied over from the wrong slide. But yeah, it's the same thing. You get the underlying value, but you call .run once you wanted to remove it from that transformer context. Okay, extensible effects. You can see I'm running out of creativity with these GIFs. I picked the first thing that showed up with extensible. It was Popeye. Not very applicable to this context, but again, getting lazy. Extensible effects. So I think I asked this question. Maybe like one or two of you were familiar with the concept of extensible effects before. So I'm not super familiar with its implementation in Haskell, but in Scala, there's something called the F monad, which utilizes the CATS library, which is an alternative to the Scala Z library. Functional programming library. And what the F monad says is that, oh, well, first, the problem there. So the problem with the monad transformers can anyone guess what the problem might be? Let's say you're working with your team members on different modules of something, and you're trying to use these monad transformers. Does anyone have an idea as to what problems you might run into? So the problem with the monad transformer is that type signature does get quite abhorrent, and you end up with these nested monad transformers that are not compatible with very similar type signatures with just things flipped around. So if you have basically a writer T, and then you have a reader T, and then these nested transformers, the order matters. So if you're working on a module, and then you choose a particular order that might have been just fine in a different order, and then your teammate chooses something else, or you're trying to develop a library to use internally, how do you choose the ordering there such that you don't have to have this basically skeleton or some sort of, you don't have to manually try and merge those cases together, because they won't be able to, you won't be able to, use like for comprehensions if they're not the same type signature exactly. So again, the ordering matters, and that becomes a problem when you have many different people working in different ways. Is that you can't compose the code in the same way because of that ordering that shouldn't matter but does matter. So what the fmonad attempts to do is basically make the ordering irrelevant. So it's a construct similar to the monad transformer in that you can have several contexts, monads, contexts present, and be able to just map or flat map or use a for comprehension over just that construct without having to do like the nested operations, flat maps, maps. So it's similar to monad transformers in that way, except it doesn't have the ordering in the same way. So the fmonad says basically you have these three contexts. For example, you have a reader monad, writer monad, and an either monad. And if you define an fmonad that is based on those three contexts, it won't matter what order those are used in. So if this other guy's using the same three contexts in an fmonad, I'm using the same context, the same monads, and we're using different orders, it doesn't matter. They're the same type of fmonad. Does that make sense? Okay, great. So this is the syntax provided by the fmonad in Scala. And you'll see first thing you have to do is define these partially applied types to be able to define the stack you're using with the fmonad. So basically in this example, we're using this a reader, a writer, and an eval. So eval, I didn't go over eval. So these are actually using the cats library. The eval is just saying you have it's a monad that you're saying you have this this value that's being computed lazily is all that's being said here. So you have those three contexts that you're forming this stack with, and then you're using that stack to define the type signature for your fmonad. So you'll see we're defining this program function here, method, that's saying it's going to return an fmonad of type R, and you're saying you have this concept of these contexts with the reader, the writer, and the eval. And then you have this for comprehension utilizing implicit syntax available with the fmonad that you'll see. So the tell in that first one is saying basically each of these is constructing an fmonad of the same type, just basically with all those contexts empty for all these values. So that first one is saying the tell is an implicit method available from the fmonad, and it's saying construct this fmonad with these available contexts, just providing the writer context. So the tell there is saying we're going to provide the log value, a log value first. So it's basically that first line is just initializing a log value for this overall fmonad, saying running P1 here. And then the second line you'll see there is this ask functionality, this syntax is also just implicitly available with the fmonad, which is saying, okay, now we want to add the reader context for this fmonad here, because we did define that type signature as saying we have a reader available as a part of this type signature, this fmonad. So you're going to provide that with that second line, and it's saying, okay, we're going to be asking for this pair of integers. That's what we're going to be using to configure this fmonad, this value. So that's what we're saying in is here. So that's saying we're providing that reader context, and we're looking for 2 integers in a tuple. So that's what in is. The third line is saying, okay, so we want to add more to that log context. So we're adding another line saying another string to that log, that writer log value that says just computing this value. And basically what we're doing in this method here is we're going to be taking the first value and raising it to the second value. So that's what that second log value is going to append. That's what that's going to say. And then the fourth line is actually just saying what we want to do with those values. So the delay is applying that eval context, which is saying lazily compute this. So that's when you actually get to the meat and the bones of what this is doing. So you're providing each of these is providing one layer of that context, and it doesn't matter the order in which you're applying these. You can see that we applied the writer context several times, and it'll just all add that together into one writer. So then you have the delay, which is actually using those asked for values and computing something. And then you have one final additional log there saying what the result is. So this yields this fmonad of these that has these various contexts available in it, as well as the actual value you want, which is this integer. And if someone else had a similar method somewhere defined to provide a value with the same contexts irrelevant of the order applied to them, it would be composable with this. So you could take this value returned from this, as well as the other value returned from someone else's code, and use them in a for comprehension, and it wouldn't matter the order in which these monads or contexts were applied. Does that make sense? Oh, wow, that made sense. Fantastic. Was not expecting that to make sense. Okay, so that is what the fmonad aims to achieve. I might actually give you an example of this actually running here. Let me see if I can. That's the end there. Let me see. I'll risk taking this out for a second here. Oh, God. Oh, beautiful. And there's no way you can read that. And I can't read that. Okay. Is that visible to everyone? Okay. So this is very similar to what that was showing a second ago in that slideshow. So you'll see that P1 is basically defined the same as that example, where you're just you have these 3 contexts. Check this out. You have these 3 contexts available, these 3 monads you're working with, the reader, the writer, and the eval, and all that method is computing is basically taking that first value you're asking for and raising it to the second value, and that's all that's really doing. But it has these contexts, these monads available for logging and for dependency injection and for lazily computing. So that's the same as the example shown. And P2 does something very, very similar, except it just takes the second value and raises it to the first value. Otherwise, it's the exact same. And then P3 is composing those 2 fmonads. So you'll see in that second example there, I actually don't start off with a log. I don't start off by providing anything for the logging the writer context. I start off with the dependency injection, whereas the first one starts off with that tell, which is applying a log value to that writer context. So the ordering is different, but it doesn't matter. You'll see in P3, we just use a simple for comprehension to compose those. So you take that first monad, the first F monad, compose it with the second one, basically saying take the underlying values and just add them together. So the integer resulting from the first one plus the integer resulting from the second one, and just add those together. And then that'll yield a new F monad of the same type. It hasn't changed. You still have those 3 available monads in context available. And then to actually utilize that, you see the run defined below. You'll take that P3 and you'll call these successive methods on it. So run reader, run writer, run eval, run. And that will actually yield the final results. I think it actually will yield a pair. Oh, let's see here. Let me just run this. I kind of just threw this together a second ago. Let me see if I can just, there we go. Let's do test run. Okay, so you'll see the final result of actually calling all those successive values, those successive methods. You call it the run reader, you call it the run writer, you call it the run eval, and you call it just run. And you'll see the end result, in this case, is just a pair, with the first value actually being the value returned, and the second value being the list of strings that you're accumulating as the log value in the writer monad. So that's what the final results is there. Any questions on that, on actually computing the value on this? Yeah, one sec. So the type signature on all 3 of those is just the just that F monad of type R and int. So the right value, the second type parameter is the value actually returned, and the first one is composed of those partially applied types, where you're saying the monads that you're composing together. No, so yeah, that's what's saying. You're saying with F monad that those are the types you're operating on. So you'll see. Those are the 3 contexts, the 3 monads you're working on, and that's what it's defined at the very top there. Can't see this again. Right there. Yeah, so that's just a shorter syntax, so you don't actually have to use like the lambda defined types using yeah.
So is that a type level list?
Sorry, right?
Is that list a type level list?
Yes. Yeah, that's all that's being used for. And actually, I can show here that this is another case where the ordering doesn't matter. One sec. So I can take that, this stupid new Mac keyboard. So I just switch those around. So first you'll call run writer, then run reader, and it'll work the same. It should, well, let's see. Maybe I'm lying. Run 2, and yeah, same thing, same value, just called in different orders. So yeah, that's the overall benefit of you're getting from the F monad is that when you're constructing it, it doesn't matter the order at which you're providing these contexts, these monads, and when you're composing them with other examples, it doesn't matter the order in which those were defined. And then when you're decomposing it, it doesn't matter the order in which you do that. Another question?
Yeah, keep it back to code. So when you're defining like your P1 or P2, is it implicitly knowing that it's constructing that monads? Like if you just drop right into the word comprehension and start using readers and writers, so at what point does it infer from
Oh, so yeah, the ask, tell, and delay are methods provided by that F monad library. So each of those is returning an F monad of that type signature, basically with all the contexts empty except for the one defined. So the ask one basically is saying we're having this whole F monad of all these contexts, all of them empty except for, since it's we're doing the ask, we're going to provide the that reader context. And then, so all those lines yield the same type signature, just with all the context empty, except for the one being applied. So the tell one just provides the writer context, and the delay provides that lazily computed context. So yeah, each of those have that F monad type signature. Okay, so yeah, this is I'm sure a lot of syntax I'm not. A lot of syntax to get familiar with. I'm not actually super familiar with it myself. I haven't used this too much in actual production code. But it does allow you to greatly simplify and aid readability when you're dealing with these nested monad types. But this is a very quickly evolving, I guess, kind of field, and a lot of people are putting a lot of thought into how to compose these things when you have these nested monads in this way. So it's very quickly evolving. But yeah, that was basically all I had. Any further questions regarding the F monad and the examples just given? So yeah, I believe so. I'm not, again, super familiar with the more detailed ways of composing these things, but I believe so. I believe you just have to use this and then add on to it the empty context that you're trying to add somewhere else, and then basically it'd just be empty for this case, and then the other thing you're composing it with would provide that. All right. Yeah, so if you're interested further in this, it's fairly well documented. If you're looking into if you're working in Scala, you can check out the F monad library, and they have decent documentation for how to work with these, as well as showing you the default effects available, as well as defining your own effects. So yeah, you can look there for further information. It's pretty well documented. All right, thanks.
All right, thank you, Dan. That was awesome. Really appreciate it.